Welcome to lesson 5.6, titled Related Rates. And in this lesson, we're going to be looking at applications for what you just did in 5.5, applications for implicit differentiation. And if you look, there are some guidelines for what we're going to call related rate problems. So I'm not going to worry about going through these steps before I start my first example. I'm just going to keep referring back to this list. I would suggest read it over by yourself first, and then as I go through examples, I'm going to follow this exact process 1 through 5. So if you look at easy example 1, it says the width of a rectangle is increasing at a rate of 2 centimeters per second, and its length is increasing at a rate of 3 centimeters per second. At what rate is the area of the rectangle increasing when its width is 4 and its length is 5? Thinking about the guidelines up top, first thing that was suggested was draw a picture. And for this problem, we'll draw a picture of a rectangle, always labeling variables that could come into play with our problem situation. And step 2, we wanted to list all rates and quantities that we know. And here's where a new situation comes into play, this idea of rates, things that are changing over time. And we have 2 of those in this problem. We know that our length is increasing 3 centimeters per second, and our width is increasing 2 centimeters per second. So listing out our known quantities, we have the change in width versus time is equal to a positive 2 because it's increasing. And we know the change in length with respect to time is a plus 3. And we also know our main goal, which is to find the rate of change for the area of this rectangle, which let's go ahead and call that change in area dA versus dt, when the width equals 4 and length equals 5. And now we've taken that entire problem situation and laid it out with all of our key values. So step 3, we want to relate all of our variables in an equation. We want to talk about area. We know our 2 variables. Our equation will be area equals length times width. Again, our goal is to find the rate of change for the area. We want this dA dt. But right now I only have A. I have A, L, and W. In order to get dA dt, that would involve differentiating with respect to time. That's how we discuss rates, is derivatives with respect to time. And so we're going to differentiate with respect to t this entire equation. We don't need to worry about taking out any variables in this problem, because as we start looking at our derivative, we have ways to describe rates for width, how that's changing, the rate of change for the length, and the thing we want to find is the rate of change for the area. Differentiating a with respect to t will give us dA dt. And think like what we did with implicit differentiation. What we're going to imply in this problem, imply all variables are functions of time. And if we think of it that way, we have L times W, these 2 functions of time being multiplied, we're going to have to apply the product rule. So the first times derivative of the second, and the derivative of W with respect to time is dW dt, plus the second times the derivative of the first. And our last step, substitute and solve. Put in all the values we know and solve for the one that we want. So we'll have that dA dt is our unknown. We know that L is supposed to be 5 at the point of time we're concerned with in the problem. The rate of change for W, dW dt, is equal to 2. Plus, the W value at this specific point in time where I want my rate of change for the area is 4, and the rate of change for length throughout the problem, dL dt, is 3. Putting that all together, we will get that the rate of change for the area at this moment in time is going to be 22, and the units, well, units for area would have to be centimeters squared over my units for time, seconds. And so let's look at one more that's a little bit more straightforward. We have a police car approaching a right-angled intersection, located here, from the north, and he's chasing a speeding car that has turned the corner and is now moving straight east. So the police car is moving this way, and the car is moving this way. When the police car is 0.6 miles north of the intersection, and the car is 0.8 miles to the east, please use a radar gun and figures out that the distance between them, which is this distance here, call it x, is increasing at 20 miles per hour. So we'll note that in the diagram. If the police car is moving at 60 miles per hour, at the instant he's measuring the rate of change for the distance between them, we want to know what is the speed of the other car. And so here we've got a lot of the parts of this already drawn out. What we're going to think of is we've got the distance between them changed, and I've already called that x. We've got this distance here for the police car from where they currently are to the intersection, and we've got our speeding car, which we'll call s. Its distance is also changing. And so here again, resist the urge to already think about those distances as being 0.6 and 0.8, because once you know that the police car is 0.6 miles away and the car is 0.8 miles away from the intersection, if they are in motion, those numbers are immediately going to become irrelevant. The police car is going to be closer, the car is going to be farther away. So we've already got our picture taken care of. So 2, we want to get our known rates and any quantities. So what we know is that the police car, their rate of change, since they're going to be moving toward the intersection, think about them moving down the y-axis, it's going to have to be negative 60 miles per hour. The rate of change for x, the distance between the two cars, is increasing, so that's a positive 20 miles per hour. And what we want to find the rate of change, the speed for this car, at the instant when p equals 0.6 and s equals 0.8. Also note that this is a right triangle. So if we have a 0.6 and a 0.8, we also know by the Pythagorean theorem, or noticing this Pythagorean triple, that the actual distance between the police car and the speeding car will be 1. So let's get an equation to relate all of our variables. And in this case, I've already mentioned it once, the equation to link them is going to be the Pythagorean theorem. P squared plus s squared has to equal x squared. And now we will differentiate with respect to time. Derivative with respect to time of this entire equation, derivative of p squared will be 2p, and then times dp dt. Just like how we talked about adding a dy dx on with implicit differentiation, everything in here, we're going to need to add the derivative of this variable with respect to time, because we are implying that every variable is a function of time. So these are all little miniature chain rule problems. This will be plus 2s ds dt equals 2x dx dt. And we'll get last step with a nice one. Substitute and solve. So we'll have 2 times that instantaneous location, that 0.6 for the police car's distance, times the rate of change for the police car, which is negative 60, plus 2 times the distance for the speeding car, which is 0.8. We don't know the car's speed, so I'll leave that one. And that equals 2 times 1, the current distance between the cars, times the rate of change there as well. Here we'll get negative 72 plus 1.6 ds dt equals 40, with 1.6 ds dt equal to 112. And ds dt, the speed of our car, will be 70 miles per hour. So let's take a look at a couple of the more involved examples, this first one being one involving an angle of elevation. And notice for this one, I've already drawn the picture for you, so if you want to take a second to copy that down, key things are, we have a camera being placed 2,000 feet away from a rocket launch, and that 2,000 is a constant. I can keep it at 2,000. So this rocket is ascending. That height is going to change, but it actually has its own function. The height, s, is 50t squared. And what we want to find the rate of change in the angle of elevation, which we can call theta. Looking at our known rates and quantities, we have that distance being equal to a constant 2,000. We have s of t, our height, being 50t squared. And what we want to find is the rate of change for theta when time equals 10. So if we want to get our equation now, thinking about how this angle that we're looking at can relate to the two quantities that we have, this is going to have to be a trig function, and it would actually be tangent. Tangent of theta would equal the opposite, 50t squared over 2,000. Or even simplifying that, it would be 1 over 40 times t squared. And so now we'll go ahead and differentiate with respect to time. And so this one's going to turn out to be a little bit strange when we get into it. Taking the derivative of tangent of theta, that is going to be secant squared of theta, and then with a d theta dt. There's that chain rule, and there's where that rate of change we want is going to come from. Equals, and this one's nice because it actually is a function of t, so we can differentiate that without having to worry about the implicit part, and we'll get 1 over 20 t. And so we're going to get a tiny issue with the substitute and solve part, because if we're looking at secant squared of theta d theta dt, I have the unknown that I want, but this secant squared theta we're going to have to figure out. I do know the other side will be 1/20th times 10, so secant squared of theta times d theta dt will equal 1/2. What we need is, we need to be able to divide this 1/2 by secant squared theta, or that's really going to mean there's going to be 1/2 cosine squared theta. The problem is we still don't know what theta is, and we definitely don't know what cosine of theta is. But if you think SOHCAHTOA, the cosine of theta would just be the adjacent over the hypotenuse. Well, here's the adjacent, 2,000. We just need the hypotenuse, which hopefully we could see would be the square root of 2,000 squared plus 50t squared squared. And going one step further, evaluating that at time 10, which we want, we're going to end up with the square root of 2,000 squared plus 50 times 10 squared, or 50 times 100, we're going to end up with plus 5,000 squared. And so cosine of theta will equal the adjacent 2,000 divided by that square root. And so cosine squared of theta will equal 2,000 squared over this 2,000 squared plus 5,000 squared, because that's going to cancel out my square root. And so all I need to do is do 1/2 times that cosine squared value. Expanding out all those numbers, if you choose to do it by hand, you'd end up with 4 million over 58 million, which will simplify down to, all these zeros are going to be gone, and 4 over 58 will simplify down to 2 over 29, and the units on this are going to be radians for the change in the angle over the change in time, seconds. And there's our d theta dt. And finally, we're going to look at an example involving a cone. This is kind of a classic AP question. We have water running into a tank at a rate of 9 cubic feet per minute. So it's increasing by 9 cubic feet per minute. The tank is pointed down and has an overall height of 10 feet, and this base radius, base actually being located at the top, of 5. And what we want to know is, how fast is the water level rising when the water is 6 feet deep? So we've got our water down here, and think about dimensions on a cone. We are looking at our radius at any time, and we're talking about our height. And the nice part is knowing that we're talking about a change in volume with the water coming in, we're mentioning the radius and the height, we're already given the volume formula. And so we already have our picture over here. Let's go with quantities and rates here. Well, we know the change in the volume versus time. We are increasing by 9 cubic feet per minute, so this is a positive 9. Don't have anything else on any other rates. So the other big part is what we're trying to find. We're trying to find the change in the water level, which means we have to be finding the change in the height. We're trying to figure out how fast this water is moving up the container when the depth itself is 6 feet. We'll make our equation. Actually, we already have our equation. We're going to use this volume formula. But notice how in this one we're going to have a big problem. If you can already imagine differentiating this, we're going to end up getting a dr dt and a dh dt from the product rule. Well, we know nothing about this. This is a complete unknown to us. And if we're not going to be able to describe dr dt, we're going to end up with more variables than what we want. We just want that dh dt to be our single unknown. We need to get r out of this problem. And so this one takes a little bit of geometric thinking. What we're going to have to think is, at any point when we look at this diagram, the level of the water and its height forms a right triangle. And if this container gets all the way full, it forms a right triangle with one leg being 5 and the other one being 10, the radius of 5 and the height of 10. And notice how no matter where I put that water level, we're going to be dealing with similar triangles. And thinking about how similar triangles work, everything in this problem is going to be proportional, and the radius will always then equal 1/2 the height. When it's full, the radius is 5, the height is 10, and it's going to apply anywhere along this cone. So thinking about that, our volume actually becomes 1/3 pi times 1/2 h squared, which will simplify to, that 1/2 squared will be a 1/4, so I'll get 1/12 when I put that with the 1/3, pi h cubed. And now we can take our derivative and get derivative of v dv dt equals, and we don't even have to apply product rule or anything, we're just going to be differentiating this h cubed. 3 times the 1/12 will give us a 1/4 pi h squared and a dh dt. And we can substitute everything we know. The volume's changing by 9. This 1/4 pi, our height level we want to look at is 6 squared dh dt, and get rid of that 1/4 and make it 36 by multiplying 3 by 4. This will be a 36 pi over here, and dh dt will equal 1/pi, which we could turn into a decimal if we want, or we can just leave it and say that this is going to be feet per minute. And that'll do it. Only thing left is for you to practice, so please make sure, review and summarize these examples, make sure you're comfortable with the process, and move on to the practice. Thank you for watching.